So good job, guys. You have already learned things about how to interpret these trees. So you even know what they're called. Good job. Yeah, this one would be a cladogram because there are these branches, but they don't have numbers. So when you look at this, then you're like, oh, these two are more closely related to each other than these two are because these are shorter than these. And that's how you normally would interpret that, except that for cladograms, that's not the case because there are no scales here. Maybe the scale would be like somewhere over here, kind of like a map that the scale is to the side. Then if there is a scale somewhere, then that would mean that these two are more closely related to each other than these two are to them. Um, but because there is no little scale anywhere, then you can't say that. You just say this is related to this is more related to this, and then that's it. Not that these are closer than these. Then this one, the little numbers, yeah, that's an additive tree, which would mean like this guy is the most different because so let's say this bird is more different from the ancestor that generated that and that than this one is. So this is done by counting the mutations, and I told you before, we don't actually, often we don't have the ancestor, but you could see how much these sequences agree, and then wherever they agree most, then we say, oh, that is probably the ancestor to all of these. So the way we interpret this is that this is more different from this ancestor than this is different from the ancestor here. All right, so yeah, this is an additive tree. And you might have noticed, these guys, they are like these right angles. Okay, these are right angles too, but they are tilted. And what's up with that? And nothing's up with that. It's just style. You throw this in a computer, and then the computer will draw however you specify it. And then this one here has the time scale, which is an ultrametric tree. So these guys here normally are in millions of years. And then there will be an exercise where I'll ask, when did the ancestor to these two birds live? And then, okay, so the two birds are today. And then when did the ancestor or cease existing? So it lived between this timing point and here. So the ancestor to these two guys is this one. When did it live? Well, it started existing when there was this speciation event here. So it lived between 2 and 3, whatever the scale is, but often it's millions of years ago. Okay, so the speciation event was 2 millions ago, to whatever the unit is. But when did this guy live? It lived between that and that. So that and that. And this tree here, it's showing you a rooted tree, but it doesn't have a time scale. It doesn't have the numbers. So you could say that this is a cladogram because it's still showing relationships. And yes, this is a little shorter than that, but maybe this was just a matter of style. And this figure is here to show you the difference also between that and that. In an ultrametric tree, all your species have to be lined up with this is today. So if we did like this, an ultrametric tree, then that would imply that, so this has to be here. Maybe you have that fossil, but normally an ultrametric tree, they will be all lined up at the present day. So here I'm telling you what the differences are. So there are differences in the angles, that this is like turned sideways in a way in comparison to that. And then the orange bird is an extra thing here, which would be an outside group to root this tree here. And yeah, you already know about the edge or branch length. So good. You already concluded on that. And our cladogram can be rooted or unrooted. And it's like all the other phylogenetic trees, is showing you the relationships. So since I spent so much time earlier and you guys were getting this idea, I guess I can go through this more quickly. So the additive, they have the little numbers. This one is a weird one. There should be a scale somewhere. It gives you the clue that it's additive because of the little lengths, but I would feel uneasy calling this one an additive because of the lack of scale. So this is a tricky one. And okay, autometric. So at this point, you might wonder, how do we know, how do we count the time if we don't have these ancestors to have their DNA to then count that? So when you have your sample, you can count time by carbon dating, but when we are doing phylogenetic trees, we actually have only these samples, and we're going back in time by how many mutations they accumulate. I was last night thinking, how can I make an analogy about this? And I thought, okay, you have the original cars, they were like the bare bones, they only had the things they needed to work. And then they over time, there were mutations, right? And now you have the self-driven cars. So uh, normally there were like features added, but in evolution, if a feature is not needed, it can also get lost. So the way we are counting time is by how many mutations have accumulated. And so that we don't confuse time with how much more fit an organism was, those mutations we count are neutral mutations. So we say that the evolution is proportional to the accumulation of mutations, but we call this the molecular clock, the accumulation of mutations, but they have to be neutral. Otherwise, you are counting also effects of fitness. So this mutation made things more or less fit than the other mutation. But a neutral mutation, there was a change in DNA that didn't make something better or worse. It was just a change. Most of them would be non-coding DNA. We'll elaborate on that in the future. So the molecular clock relies on neutral mutations, and the neutral mutations don't make things more or less fit. So in the chat, what type of tree is this? Yeah, good job, guys. Yeah, it is the ultrametric because you're like, oh, it has a time scale. So yeah, ultrametric tree. Good job. And I also like showing this tree because people say that humans evolved from monkeys. Well, not quite. We evolved from a common ancestor. So it's like, okay, so here are monkeys, and then here are the apes. So we are closely related to chimpanzees. So these guys are apes. These are monkeys. I actually don't even ask me what's the difference between monkey and an ape. I don't know either. All I know is exactly what you guys are looking at here. You might know this more than I do. But if you want to hear some story about teaching evolution, there is a movie. It's like one of my favorite movies. It's called Inherit the Wind. So I don't know if you've ever heard of that. It's about a monkey trial. So there was a biology teacher, science teacher, I don't know. And this is, the movie is old, it's in black and white. A monkey trial is real fact. This happened. The guy was teaching evolution and then he was sent to jail. Anyway, watch the movie. It's fun. So in terms of tree, we have a common ancestor. Let's see. So in here, is our common ancestor, right? So there was some species that lived between 50 and 35 millions of years ago, whatever that species started existing here, and then in here it diverged into the monkeys and the apes. So here is when the ancestor of monkeys and apes ceased existing because it speciated into this different, or speciated into that and the ancestor of those. All right, so last slide of this is, okay, how do I tell a computer to draw these relationships when I'm typing code? And this for this class is mostly curiosity because we're not programming, but some of you might be programming, might be in the applied math route, who knows? So there's something called Newick representation. And what it does is it uses parentheses to show relationships. So see, the innermost parentheses are the two most closely related entities. Then you have this third one that joins in there. And then these guys here. So you can compare this and see how the parentheses have produced this tree. And then in homework, I will ask you this. In the exam, I might not, but if I do, this is how you interpret it. It's by looking at the parentheses, the closest parentheses, and I make them color coded to make it easier for you to follow. The computer does, you don't type it color coded, but for us, it's just easier to see it. So good. Questions about phylogenetic trees? I have to say, I'm proud of you guys for responding the names and figuring out the difference between cladogram and additive trees. So I was happy to see that. So thank you for that.